Hello. In this video, we're going to learn about electron configuration and how electrons occupy orbitals. So first, let's talk about what electron configuration is. So electron configuration is a simple way of writing down the location of all the electrons that are in an atom. It's kind of like the address book for the electron location. So for example, hydrogen only has one single electron, and that one electron occupies the 1s orbital. The electron configuration for hydrogen is therefore 1s1. The superscript, this 1 on the right side here, represents the number of electrons that are in that orbital. Since hydrogen only has one electron, and that's in the 1s orbital, the 1s orbital has a single electron in it. The 1s represents the orbital. So hydrogen only has a single electron that's in the 1s, so its electron configuration is 1s1. Helium has two electrons, and both of those electrons are in the 1s, so its electron configuration is 1s2. Lithium has three electrons. Two of those electrons are in the 1s, but remember that the 1s only holds two electrons, so the third electron of lithium has to go in the 2s. So the electron configuration for lithium would be 1s2, 2s1. Notice that I'm giving the location of all three of the electrons that are in lithium. If I were to add all the superscripts together, that would give the total number of electrons that are present in that atom. Remember we talked about the energy of the orbitals, and we said the lowest energy orbital is the 1s, so that's the closest to the nucleus, followed by the 2s, right? Each of these hold two electrons, followed by the 2p. There are three subshells of 2p, each hold two electrons, so that's a total of 6 electrons in the 2p. The 3s holds two electrons. The 3p's together hold 6 electrons, just like the 2p. The 4s holds 2 electrons, and the 3d's together hold 10 electrons, 2 in each of the 5 subshells. And this continues on and on. So let's go ahead and write the ground state electron configuration for chlorine. So on the periodic table, chlorine is number 17, which means that it has 17 electrons. So when we start filling in the orbitals for chlorine, we begin with the 1s. We put 2 electrons in the 1s. Then we put 2 electrons in the 2s. That fills up the 2s. Then we put 6 in the 2p. Each of the 2p's gets 2. So far, we've added 10 of the 17 electrons. We add 2 in the 3s. That's 12. And then we have 5 more electrons left that go in the 3p, since the 3p can accommodate up to 6 electrons. So the electron configuration with chlorine then would be 1s2, right? Because we put 2 in the 1s, 2 in the 2s, so 2s2, then 2p6, because we can put 6 in the p's. So far, we've used 10 electrons of the 17. Then the next orbital is the 3s, so we put 3s2, and then so far we have used 12. There's 5 more electrons which go in the 3p5. So this would be the electron configuration for chlorine. Notice that I do not separate each of the orbitals by a comma. I just write them all next to each other. Now let's look at drawing orbital diagrams. So orbital diagrams are another way of representing the electron location inside of an atom. Orbital diagrams give us a little bit more information than electron configurations do, because we're actually drawing each orbital and showing how the electrons are put inside of them. So the orbital diagrams show the electrons as arrows inside of a box that represent the orbital. So here I have 2 electrons in these orbitals. One is arrow up, the other is arrow down. These arrows pointing in different directions represent something called an electron spin, which is just a property of an electron that we're not really going to go into detail about, but you just have to know that within the same orbital, 2 arrows cannot point in the same direction. One has to point up, the other has to point down. And by convention, we always begin with arrow pointing up. Okay, so this here is the orbital diagram for helium. Helium has 2 electrons. Both of those electrons are in the 1s. So this box represents the 1s orbital, and I put 2 arrows inside of it. Notice also that when I label the orbital, I do not write 1s2 because that's for electron configuration. I just write 1s because the name of this orbital is 1s. Okay, so students a lot of times confuse electron configuration with orbital diagram and actually label this as 1s2, but it should just be 1s. Okay, so what are the guiding principles behind writing the electron configuration and drawing the orbital diagram for an atom? We follow the Aufbau principle, which states that electrons must occupy the lowest energy level first before filling the higher levels, which means that when we add electrons, we always begin at the 1s, we fill the 1s, then we go to the 2s, we fill the 2s, then we go to the 2p, we fill the 2p, then the 3s, and so forth. So we go to the lowest energy orbital first. And if you remember, we talked about this in a different video, that electrons are most stable when they are in the ground state, which is the lowest energy state. The next guiding principle is the Pauli exclusion principle. The Pauli exclusion principle states 2 things. One, that orbitals may hold no more than 2 electrons, and the other is that those 2 electrons have to have opposite spins, which means that they have to point in opposite directions. Okay, so we saw for helium in the last slide that those 2 electrons, one pointed up, the other pointed down, and no more than 2 electrons are allowed in an orbital. And then the third rule is called Hund's rule. And Hund's rule states that when we're filling orbitals of equal energy, the electrons fill them singly first with parallel spins. So this refers to, for example, the 3p orbitals that we have. Remember we said there's a px, a py, and a pz that are all degenerate, meaning they have the same energy. When we're filling those, we put 1 electron in each of those boxes at a time before we pair the electrons together. And the reason for that is because electrons repel each other, right? Because they're both negatively charged, and so they prefer to be as far from each other as possible. So when we have 3 orbitals that are all the same energy level, for example, if I have 3 boxes of the 2p orbitals, okay, electrons like to fill these one at a time, so 1 electron in each of these with parallel spin. Parallel spin means they're all pointing in the same direction. We do this before we put another electron in each orbital. Okay, so now let's go ahead and draw the orbital diagram for nitrogen. On the periodic table, it shows that nitrogen has 7 electrons. So we start, remember, filling in electrons with the lowest orbital first, right? So we put 2 in the 1s, right? So that would be following the Aufbau principle by putting electrons in the lowest energy level first. So we put 2 in the 1s, we put 2 in the 2s, that's 4 electrons, then the other 3 electrons go in the 2p. But remember, based on Hund's rule, we have to fill these one at a time. So we're going to put one electron in each of the p orbitals. So we put 2 electrons in the 1s, right? Because 1s is the lowest energy state and it only holds 2 electrons. Notice my electrons have opposite spins, right? That's because of the Pauli exclusion principles. No more than 2 electrons are allowed in each orbital and they have to have opposite spins. The 1s is now filled. I put 2 electrons in the 2s. There are 3 more electrons left. I put them in the 2p, but I fill those one box or one orbital at a time. They are degenerate. The 2p's all have the same energy, and because electrons repel each other, they prefer to each occupy one of the 2p orbitals singly before being paired. Its electron configuration is 1s2, 2s2, 2p3. For electron configuration, notice we do not give the px, py, pz separately. So that is an extra piece of information that we get from the orbital diagram by actually showing how the electrons are occupying each of the orbitals. All right, so far I've been showing you how to draw the orbital diagram or write the electron configuration using that energy diagram that I showed you, where we start off with the lowest energy 1s, then 2s, then 2p, and so forth. But we can actually use the periodic table to write the electron configuration of an atom based on its position on the table. So you actually don't even need to memorize the order of the energy of the orbitals. You can just use the periodic table to draw the orbital diagram or write the electron configuration. So let's go over the rules for writing the electron configuration for an element. The first thing you want to do is to find the atomic number of the element from the periodic table. Remember that if it's a neutral element, then the number of electrons is equal to the number of protons. So the atomic number will equal to the number of electrons. So for example, nitrogen has atomic number 7, which means that it also has 7 electrons as a neutral atom. And then what you have to do is you have to note that each orbital holds only 2 electrons. Remember the s's, they only have 1 orbital, so they only hold 2 electrons. The p's have 3 orbitals, right? There's the px, py, and pz subshell, so they hold a total of 6 electrons. The d's have 5 orbitals, they hold 10, and the f's have 7, so they hold 14. And then what we do is we use the order of the filling that's represented by the blocks on the periodic table, and we go across the periodic table from left to right, top to bottom, and distribute those electrons in the appropriate orbital. So I'm going to show you how that works. So first, you have to remember where each of the blocks are. These first 2 columns are the S block, plus this very last column or the last box where hydrogen is, okay? So the S box is the first 2 columns of the periodic table plus hydrogen. The next block is the P block. The P block is the last 6 columns of the periodic table, not including helium. So remember we said the S block was the first 2 columns plus helium. The P block is the last 6 columns. So notice that the main group elements are made up of the S and the P blocks. The next block is the D block, which is the 10 columns that make up this transition metals over here. Okay, so these are the D blocks. And remember we said that the Ds actually hold 10 electrons total. There are 10 columns here. We said that the P's hold 6 electrons total. There are actually 6 columns here. And the S's hold 2 electrons, so there are 2 columns here. And then our last block is the F block, and the F block is the inner transition metals. Remember we said that the F orbitals hold a total of 14 electrons. So these are the 14 columns here are the 14 electrons that occupy the F orbital. So here's just another representation of the blocks. The S blocks are these first two columns plus helium. The P blocks are these last 6 columns. The D blocks are sandwiched between the S and the P block, and the F block is this group 2 rows at the bottom. Okay, so then what we do is we use this order of the filling we said, right, to distribute the electrons. And note that as you're filling the S and the D blocks, the S and the D blocks correspond to the row number as you're filling them, but for the D blocks, it's actually row number -1. And for the F blocks, it's row number -2. So the fourth row transition metals actually fill up the 3D orbitals. So what we see here is this is row number 1. That's where the 1s is. Row number 2, the 2s. Row number 3, the 3s. Row number 4, the 4s. So for the s's, the row number actually corresponds to the filling of that orbital. Same thing with the p's. This is row number 2, so we fill the 2p's. Row number 3, we fill the 3p's. Row number 4 is the 4p's. But then notice that as we go to the d's, the 3Ds are actually in the fourth row, right? So we have the 4S and then the 3Ds and then the 4Ps. And then for the Fs, remember that the Fs actually start here, okay? They start at the 6th row. So the 4Fs are in the 6th row. So it's 2 minus, or the row number -2 for the Fs. For the Ds, it's the row number -1. So 4th row is the 3D, 5th row is the 4D, 6th row the 5D, and so forth. So let's go ahead and find the electron configuration for sulfur. So sulfur is right here. It has 16 electrons. So we start off by filling at number 1 here. We start with the S block. So first we start with the first row. 1s2 takes us to helium. And then we go to the second row. 2s2 takes us to beryllium. And then we cross over to the P's. This is 2p6, brings us to neon. Then we go to the third row, 3s2, and then we cross here, 3p4. So the electron configuration for sulfur is 1s2, right? 2s2, 2p6, 3s2, and then 3p4 because it's the fourth column over. Now let's look at the electron configuration for manganese. So again, we always start off at the 1s, right? So 1s2, 2s2, right? 1s2 takes us to helium. 2s2 brings us to beryllium. Then we go to the P's, right? You always go across the row from top, across from left to right, and then down. So then 2s2 and then 2p6 brings us to neon. And then we go to the next row, 3s2, right? And then 3p6 brings us to argon. And then 4s2 brings us to calcium. And then remember, this is the 3Ds, right? So the first row of the Ds is the 3Ds, even though it's in the fourth column. So it's 3D, 1, 2, 3, 4, 5, 3D5. All right, so now let's go ahead and do one more example. On this slide, we're going to find the electron configuration for bromine. Okay, using the periodic table. I know that I've hidden all these, you can't see them, but the bromine is right here and I circled it. So we start off at the top with the 1s, so 1s2, okay, and then we go to the next row, 2s2, right? So 2s2 takes us right here. Then we go across to 2p6, and then 3s2. So then 2p6, then 3s2, and then we cross over to the 3p's, so 3p6, and then we go to the next row, right? That's the 4s2, and then 3d10. Okay, so then it's 4s2, and then 3d10. And then notice that bromine is the fifth one over. So then it's back to the 4, so 4p5. Just again, notice that the D's are in the fourth row, right? 1, 2, 3, 4, but it's the row number minus 1. That's where the 3 D's are. If I were to add up all of these superscripts together, that would add up to the number of electrons that bromine has, which is 35. So the 5 plus 10 plus 2 plus 6 plus the 2 plus the 6 plus 2 plus 2 is equal to 35. Okay, so now we're going to look at two exceptions to the electron configuration rule. So the expected electron configuration or orbital diagram for chromium and copper is for chromium, this is the 4s, so we put 4 in the, or 2 in the 4s and 4 in the 3ds. For copper, right, this is the end part of the electron configuration. 2 goes in the 4s and 9 goes in the 3d. This is the expected electron configuration. So if I were to write the electron configuration or the orbital diagram, it would come out like this. But in reality, the real electron configuration or orbital diagram takes one of the electrons from the 4s and places it in the 3d. Likewise for copper, one of those 4s electrons is placed in the 3d. The reason this happens for chromium and copper is that the d orbitals are more stable when they are half filled or if they're completely filled. Notice that in this form, because these d orbitals are either half filled or completely filled, they are more stable. Now, any orbital that's half or completely filled is more stable, but remember that with the 2p's, for example, this doesn't happen because the energy difference would be a lot, right? So here to go from the 4s to 3d, a little bit of energy had to be invested to move that electron over to the higher orbital. But once we get this to be half filled, overall the energy level comes down lower. Okay, so the expected electron configuration for chromium is actually ends in 4s1, 3d5, and for copper, it ends in 4s1, 3d10, rather than the expected that we looked at up here. Okay, and this actually is also true for molybdenum, which is right underneath chromium, and it's also true for silver, Ag, which is right underneath copper. So they are also exceptions to the rule for the same reason that the half-filled and the completely filled d orbitals are more stable. So the expected configuration for chromium is 2 in the 2s, or 2 in 1s, 2 in 2s, 6 in the 2p, 3 in the, or 2 in the 3s, then we fill the 3p's, okay, and then 2 in the 2s's, and 1, 2, 3, 4 in the 3d's. This is what we would expect. But in reality, what actually happens is that 1 goes in the 4s and 3 go in the, or 5 go in the 3d's to make the d orbitals half filled. Because this half filled d orbitals that have this configuration and 1 electron in each actually overall gives the entire chromium atom a lower energy. And then for copper, the expected configuration is 1, 2, 3, 4, 5, 6, 7, 8, 9 in the 3Ds. This is what we would expect. But in reality, what happens is that only 1 goes in the 4s, but 4 or 10 go in the 3Ds. So one of those 4s electrons actually jumps up to the 3D. And the reason for this is that a completely filled d orbital overall brings down the energy of the copper atom, even though a little bit of energy had to be invested to move that electron from the 4s to the 3D. It makes up for it and more. Now, there is a short version, which we call abridged, or the shorthand version, or the short version electron configuration. In this case, rather than starting and writing everything beginning with 1s, right, 1s2, 2s2, 2p6, and so forth, we start with the symbol of the noble gas that's in the previous row, and then we follow it with the remaining additional configurations of the electrons. So for example, with manganese, if we wanted to write the abridged or the shorthand electron configuration for it, here is manganese here. We go to the noble gas that's before manganese, which is argon. So we put argon in brackets, and then we follow it with the rest of the electron configuration up to manganese. So then after argon, it's 4s2, then 3d5 to get to manganese. So this is called the abridged or the short version electron configuration. It's the preceding noble gas in brackets followed by all the other remaining electrons that are in between that noble gas and the element that we're finding the configuration for. So here are some practice problems for you to do on your own, and then on the next slide, you will see the answers. So you can pause it and solve this on your own. And here are the answers to that practice problem.